Alright, previously we studied how to describe firms' technologies, and we discussed how to classify firms' production technologies in terms of return to scale and in terms of elasticity of substitution. Okay, and now with that description in hand, we move on to the second topic in the theory of the firms. Okay, that is the firm's market behavior. Okay, so in this video, we begin our study of the firm's market behavior under the two assumptions on the price factor, the same assumptions as we did in the in consumer theory. Okay, so we first assume that information about the price factor is publicly available. Okay, so the price of a good 1 from price of a good 1 to price of a good L, every individual is on the same page. And the second, we assume that comparative assumption. So the market price is determined by the two economic forces of market, aggregate demand and aggregate supply. So price is determined by the intersection between the two curves, rather by the individual behavior. Okay, so in other words, each individual has no market power in determination of the price factor. Okay, so price factor is independent of the firm's behavior. Okay, and the way to describe firm's behavior is the same as before. Okay, so just as we describe the consumer's behavior as the choice of one bundle, we describe the firm's behavior as the choice of one production plan. Okay, so the factor Y. Okay, so considering the same market structure and considering the same assumptions on the price factors, now we think about the optimal production plan. Okay, so before doing that, we have to think about in which sense we call that optimal production plan. Okay, so the first behavior assumption we can make on the firm's behavior given this price factor P, it is natural to assume that firm chooses one production plan so as to maximize firm's accounting profit. Okay, so it's quite a natural assumption, especially in classic microeconomics. Okay, and the way to express the profit in terms of production plan is, so it can be written as the dot product between the price factor and the production plan. Okay, the way to understand this expression is, so think about the two commodities. Okay, remember, in the description of a production plan, negative sign means the firm uses that commodity as an input, and positive sign means that firm produces that good as an output. Okay, so in case of two commodities, think about this production plan, negative 1 and 2. So that means the firm uses the first input, the first commodity. So with the 1 unit of the first commodity, the firm can produce 2 units of the second commodity. Okay, so by choosing this production plan, if we think about the corresponding profit, it's going to be the dot product. So if we take the dot product with the price factor, then it gives us negative P1. So that can be understood as the cost of employing this input. So 1 unit of the first good. Okay, so that is a corresponding cost. And the corresponding revenue is going to be a second term, 2 times P2. So it can be understood as the revenue from producing and selling 2 units of the second good to the market. Okay, so the way to express the firm's accounting profit is the dot product between the price factor and the production plan. Okay, so just as in consumer theory, so when we derive optimal consumer behavior, So we derive optimal behavior from the two optimization problems, utility max and expenditure mean. Okay. And similarly, we can derive firm's optimal behavior from the two optimization problems, profit maximization problem and cost minimization problems. Okay. And in this video, let me focus on the profit maximization. Okay. And then this problem can be written as maximizing profit, so P dot Y, subject to one constraint, because this production plan must be feasible. So plan Y should be an element of the production set. Okay. And the way to reformulate this is the if we go back to the definition of the production plan, we define the production set. If we go back to the definition of the production set, so we define the set with the with a one transformation function. Okay, so set Y is defined as the set of plans. Okay, so in case of L commodities, it's going to be L dimensional vector such that transformation function takes a value less than or equal to 0. Okay. So using this transformation function, we can reformulate the profit maximization problem into maximizing P dot Y subject to f of Y is less than or equal to 0. Okay. Alright, so now we are going to derive the optimal production plan from this maximization problem. Okay. And the solution, so the profit maximizing production plan will be denoted by Y star. Okay, and this Y star must be a function of the price vector P. Okay, because the only parameter in this problem is the price vector. All right, so by definition of Y star, P dot Y star, that is the profit by choosing. So the profit the firm can accrue by choosing this plan Y star, right, that should be larger than or equal to P dot Y, so for any other production plan, any other feasible production plans. Okay. So this notation means for all. Okay, so by definition of this Y star, by choosing this one, the firm can earn the highest profit as much as possible. Okay, meaning that this quantity is larger than so profit from choosing any other production plan. Okay, and we call this Y star the supply function. Okay. Anyway, so that's the definition of the solution. And the way to derive this is the same as before. So we employ the Lagrangian multiplier method. Okay. So the associated Lagrangian with this profit maximization can be written as L is going to be, we first put the objective function that we want to maximize, P dot Y. Okay, and we need one multiplier lambda associated with this constraint. Right, and then the so when we construct the Lagrangian, we convert this inequality into the form something is larger than or equal to 0. Okay, so to make this form for this conversion, we move this term, this transformation function, to the right hand side. So that gives me negative f of y. Okay, so that is a common way to construct a Lagrangian. Okay. Okay, good. All right, so the choice variable is going to be vector y. Okay, so the stationary condition is going to be every partial derivative of this Lagrangian with respect to y sub k, for example, should be equal to 0 at the optimal solution. Okay, so the multiplier theorem tells us if we have an interior solution y star, okay, so in this example, because in producer theory, so if we think about the production plan, some component can be negative and some component can be positive. So interior solution can be thought of as the vector whose element is bounded below and bounded above. Okay, so if every component in this vector is bounded, it can be regarded as an interior solution. And if that is an interior solution, Lagrangian multiplier theorem tells us, at this point, Lagrangian should be a stationary point. So this point should be a stationary point of the Lagrangian. Okay? So we have this optimal condition. So if we take the partial derivative with respect to y sub k, okay, then p dot y becomes p sub k. Okay? Then the second term gives me lambda times negative partial derivative of this f with respect to y sub k. Okay, and set it equal to 0. Okay, or we can set price factor, also price of a good k equal to multiplier lambda times this partial derivative. So this should hold for every k, so from 1 to L, in case of L commodities. Okay, so or in vector form, vector notation or matrix notation, we can write it as, so we can merge every condition into matrices. Okay, then so in case of two commodities, we have one condition. P1 should be equal to lambda times f sub 1. So the partial derivative of this transformation function with respect to y1, and P2 equal to lambda times f sub 2. Okay, so in the matrix form, we can write it as price vector P1 and P2 equal to lambda f sub 1 and lambda f sub 2. Okay, and then constant lambda is a scalar multiple, so it can come out like this. Then f sub 1 and f sub 2. Okay, and this factor is the gradient of function f evaluated at the interior solution, so the solution candidate. Okay, so the stationary condition can be merged and can be expressed into matrix forms this way. Okay, and the interpretation is the same as before. Okay, so for profit maximization, so profit maximizing plan, the price factor and the gradient of the transformation function should indicate the same direction. Okay, or so in case of two commodities, like in this figure, so we have a good 1 and good 2, right? Then we can divide one condition by the other. So if we divide the first condition by the second, okay, then we obtain P1 over P2, and the common lambda will be cancelled, and we have f sub 1 over f sub 2. Okay, so f sub 1 over f sub 2 is called the MRT in our textbook, marginal rate of transformation between two goods. Okay, and that determines the slope of the tangent line to the production set at the frontier. Okay, so here the projection set is given by the region between, so the region below this frontier. Okay, so every plan inside this set is feasible. Okay, and at this frontier, so at some point on the frontier, the slope of the tangent line is given by the MRT. Okay, and for profit maximizing projection plan, this MRT should be identical with price factor P1 over P2, the ratio of the two price factor, or the ratio of two prices. Okay, so where this guy comes from, now if we think about the isoprofit, so isoprofit can be written as isoprofit. So it has the same meaning as isoquant, as the isoquant gives us the so isoquant indicates the set of inputs with which the firm can produce fixed level of output, and this isoprofit is going to be a set of projection plans such that P dot y is equal to some certain level, pi hat. Okay, so it indicates the set of projection plans such that by choosing this plan, the firm can attain certain level of output. Okay, so it gives us the set of projection plans the firm can earn the same profit, okay, as much as pi hat. So in case of two commodities, isoprofit takes the form of P1Y1 plus P2Y2 equals pi hat. Okay, so it's going to be line segment, okay, straight line, having the slope negative P1 over P2. Okay, and then profit maximizing condition tells us so if we draw the several isoprofit curve, so of some level pi hat with a lower level pi hat prime and so on. Okay, and then so we gradually decrease this isoprofit up to the point, this isoprofit curve, so isoprofit line is going to be exactly overlapped tangent line to at some point on the frontier. Okay, just like just as so that is the same procedure as we find out the Hicksian demand in the expenditure minimization problem. So in the expenditure minimization problem, we pin down one indifference curve, right? And then we gradually adjust the ISO expenditure line segment, okay, up to the point, this one isoprofit expenditure line segment is going to be tangent line to this indifference curve. Okay, so at this point, okay, the slope of the indifference curve, so MRS is equal to the slope of this line segment, that is P1 over P2. Okay, so in this profit maximization problem, we pin down the firm's technology with the projection set. Okay, and then we adjust the isoprofit curve up to the point where the slope of the tangent line to this projection set at that point is exactly the same as the slope of this isoprofit. Okay, so that is a so that shows how we determine the optimal or profit maximizing projection plan. Okay, all right, or in terms of vectors, because this price vector is going to be a normal vector to the isoprofit. In other words, it is a perpendicular to this line segment. Okay, and this price vector should indicate the same direction as the gradient of function f. Alright, and then so that is the way of determining the supply function. I'll show you one example, to help you understand how we determine the supply curve or supply function from the profit maximization problem. Okay, and the value function to P and P is called the profit function. Okay, so it tells us the maximal profit the firm can attain given price vector P. Okay, so it's defined as P dot Y star of P. Okay, so in the expression of profit, if we substitute the supply function, we obtain the profit function. So it is the highest profit the firm can attain under price vector P. Okay, so highest profit attainable under price vector P. Okay, so to clarify our discussion, let me show you one example. Okay, so in this example we have 3 commodities. Okay, good 1, good 2, good 3, and the production set is given by this one. Okay, so from the negative sign on Y1 and positive signs on Y2 and Y3, we can see that this firm uses the first commodity as an input to produce the second and the third commodities. Okay, and the frontier is given by this function. So we can take this function as big F of Y1 and Y2 and Y3. Okay, so once the firm employs this amount of input, okay, and we move this term to the right hand side, so that determines how much good Y and good 3 the firm can produce. Okay, so that determines the frontier or the boundary of the production set. Okay, and we are asked to derive the firm's profit function. Okay, then the firm's profit can be written as P dot Y or 1 comma P2 and P3 dot product negative Y1 Y2 Y3. Okay, so that's going to be negative Y1 plus P2 Y2 and plus P3 Y3. Okay, so we want to maximize this expression subject to this constraint. Yeah, let me change this number 5 on the denominator to 2, because I think that simplifies our computational work. Alright, then the associated Lagrangian can be written as negative Y1 plus P2 Y2 P3 Y3, and we need one multiplier lambda. Okay, and we change this inequality into the form something is larger than or equal to 0. Okay, so we move every term to the right hand side, then we obtain Y1 minus Y2 squared minus Y3 squared over 2. Okay, and applying the stationary condition, so we take the partial derivative with respect to Y1, then negative Y1 becomes negative 1, and P2 Y2 P3 Y3, every term becomes a constant except this Y1, so we have plus lambda and set it equal to 0, because other terms go away, okay, because they are constant. And partial with respect to Y2 gives me P2. Okay, so P2 Y2, that becomes P2, and Y2 squared becomes 2Y, so we have 2 lambda Y2 and set it equal to 0. And finally, with respect to Y3, we take the partial derivative So minus lambda y3 and set it equal to 0. Okay, and from the first condition, we obtain the value of multiplier. So lambda is equal to 1. Okay, and we can substitute that value into the third and the second conditions. Then the second condition becomes p2 equals 2y2. So from that, we obtain the supply curve, supply function for good 2. So y2 becomes p2 over 2. Okay. So consistent with our intuition, it is an increasing function. If the price of good 2, market price of good 2, increases, the firm is willing to supply more. Okay. And third condition becomes, after substitution of lambda, p3 becomes y3. Okay, so y3 equals p3. Okay, and then one more thing, because lambda turns out to be strictly positive, meaning that by the complementary slackness condition, we know that this constraint is binding. Okay, so the given constraint is binding. So set this with equality, and we obtain y1 equals y2 squared plus y3 squared over 2. Okay, so with that, we can express y1. So optimal demand for input 1, so the first commodity, because the firm using this as an input, as a function of p2 and p3. So it's going to be p2 squared over 4 if I substitute p2 over 2 for y2, and p3 squared over 2. Okay, so consequently, we substitute everything in the expression of a profit. So pi of p is going to be negative y1, and p2 times y2 is p2 over 2, and p3 times y3 is p3. Okay, so profit is going to be p2 squared over 4 plus p3 squared over 2. Okay, so it's a function of price factors, because price of a good one is normalized to 1. Okay, so that is reflected in this profit function. Okay, so that's the way of finding optimal demand. So optimal production plan or supply function, and the way to find the profit function. Okay, so that is a general way of finding optimal. So that is a general way of finding the firm's behavior in terms of production function and in terms of production plan. But in the case of a single output technology, profit maximizing problem can be put as, okay, so now we need information about the price of output. That is denoted by P. So P is price of output, unit price of output. Okay, and suppose that firm produces output Q using L-1 different inputs. Okay, so here vector Z indicates so the collection of demand for each input from L to L from 1 to L-1. Okay, and vector W indicates the input price vectors. So W is W1 to WL-1. Okay, and each component indicates the unit price of input. Okay, and then the total cost of employing input Z is going to be dot product between price vector W and the demand schedule Z. Okay, so we use different formulation here. So we use production function instead of production plan. So production set to describe firm's technology in case of a single output technology. Okay, so every component is positive. Okay? So every component is positive. All right, then because firm can produce up to f of z using this input. That's the definition of the production function. So the total revenue is going to be function of a price, function of input vectors z, and the cost also function of z. Okay, and the choice variable is now the firm determines the input demand schedule. Okay, given price vectors, so price of output and input price vectors. Okay, so the usual first order condition applies to this maximization problem. So because we don't have any constraint other than this one, but usually the way to solve this maximization problem is we disregard this constraint for a second. Okay, and applying the first order condition to this expression. Okay, that's going to be partial derivative with respect to z sub k is going to be 0 for every k. So here k goes from 1 to L minus 1. So in case of L commodities. So in case of L minus 1 inputs. Okay. So in case of 2 inputs or 3 inputs, whatever, we can apply the same first order condition to find the optimal input demand schedule. So we call this optimal demand schedule as the so factor demand function. Yeah, factor demand function. Okay, sometimes unconditional factor demand function. Yeah. So why did I put unconditional here will be clearer when I talked about the so after we talk about the cost minimization problem. So from that we obtain the conditional factor demand function. Okay, because there is a this demand function is unconditional in the sense that we don't have any other constraint here. Yeah, but in cost minimization problem we have a one constraint. Okay. Great. So because the same condition applies to every k. So if we merge first the condition for good k, for input k, and the first the condition for input j, so that's going to be p times the derivative of a production function with respect to j's input. That should be equal to w sub j. So we can divide one by the other. Then the price of output p will be cancelled out. Okay, and the ratio between these two partial derivatives, that is going to be rate of substitution, technical substitution. Okay, so we have MRTS on the left hand side, and on the right hand side we have the ratio of input prices, W sub j over W sub k. Okay, so that gives us another interpretation of so another geometric interpretation for profit maximization. So if we have two inputs, so input 1 and input 2, and we have isoquant here. Okay, and MRTS measures the slope of the tangent line to isoquant, right? And W sub j over W sub k in case of two inputs, so W sub 1 over W sub 2, that is the slope of the isocost. So isocost is defined as, in case of two inputs, it takes the form of W1 times Z1 plus W2 times Z2 is given by C hat. Okay, so yeah, it takes the same form of the expenditure function. So we adjust the level of this isocost up to the point where this isocost is tangent to isoquant. Okay? And the coordinate, so the x and y coordinate of this point gives us factory demand function for input 1 and input 2. So z1 star and z2 star. Okay. Alright, so that's the way of finding factory demand function. In other words, the way of solving profit maximization problem in case of a single output technology. Okay, I mean when the firm produces single output. All right, and then in the next slide, I enlisted the properties of profit functions. Okay, and these properties are very similar to the properties of expenditure functions. So suppose that production set is closed. That means it includes the frontier, okay? Because the profit maximizing plan is determined at the frontier. So we have to make sure that that frontier is an element of the production set, okay? And it also satisfies the free disposal property. Then the profit function pi and the supply function y star satisfy the following properties. So y star is homogeneous of degree 0. And the profit function is homogeneous of degree 1. So I guess you can easily verify these two facts by yourself. So let me leave it exercise. And the fourth property, the law of supply holds, meaning that the dot product between the change in price and the change in supply function is going to be positive value. That means the price factor and the supply function move in the same direction. Okay? So if price goes up, then the y star also goes up. Okay, so it describes a positive association between the price and supply curve. Okay, in case of law of demand, we have a negative dot product. That means change in price and change in demand, indicate the opposite direction. So they move in the opposite direction. But in case of supply, they move in the same direction. So this is also very easy. It is immediate from the definition of a y star. So let me leave it as an exercise. Okay. The second and third one are a little bit non-trivial. Okay. So the second property tells us profit function is convex in the price vector P. Okay. And that is very similar to the fact that expenditure function is concave in the price vector. All right. So we're going to prove this in the next slide. And the third property is called the Hotelling's lemma. It tells us if we take the derivative of a profit function with respect to P sub k, then we obtain a supply function for good k. Yeah? So I'm going to prove the second and the third properties together in the next slide. Right? So the way to show that profit function is convex, then we have to show that, so suppose that we choose two price vectors, P and P prime, and consider its linear combination. So here alpha, so the weight on price vector P is a constant between 0 and 1. Okay, so P circle is defined as the linear combination between P and P prime with weight alpha. Okay. Then we have to show that the function's value at this linear combination is less than or equal to linear combination of the function's value at P and P prime. So we have to show this. Okay. So before proving this statement, before proving this inequality, it comes as no surprise because, if we compare the left-hand side and the right-hand side, on the left-hand side, profit function comes from the one profit maximization problem. So we have just a one maximization problem on the left-hand side. But on the right-hand side, we have two different profit functions. So we have to take into account maximization under price vector P, and another maximization problem on the price vector P prime. Because we have one more maximization problem on the right So this guy clearly is larger than the quantity on the left hand side. Okay, and we can formally prove that. So by definition of pi profit function, it tells us the highest profit under price vector p circle. So its definition is the dot product between p circle and the supply function at the same price. Okay, now I can substitute the definition of p circle. Okay, so alpha p plus 1 minus alpha p prime for p circle here, and then distributing the dot product gives me alpha p dot alpha star, and 1 minus alpha p prime dot alpha y star. Okay, then if we compare this one with p dot y star of p, because y star of p is the profit maximizing plan under p, so this quantity should indicate the highest profit attainable under price vector p, so it should be larger than this guy, because y star of p circle is a different production plan. That is optimal under price p circle, not under price vector p. Okay, but this guy is the profit function at p. Yeah, so we can make sure that this profit function is larger than this one, at least larger than this one. Similarly, if we compare this quantity with p prime dot y star of p prime, okay, that is the profit function at p prime. Okay, we can make sure this guy is larger than this one by definition of y star. Okay, so we have this inequality because each term is larger in the last expression. Okay, so the profit function is convex. So just to remind you of the formal definition of a convex function, so we formally say function f is convex if f of alpha x1 plus 1 minus alpha x2. So the function's value at the linear combination is smaller than or equal to linear combination of the function's value. So alpha times f of x1 plus 1 minus alpha f of x2. Alright, so that is consistent with the definition, meaning that profit function is convex. Okay, and the Hotelling's lemma is immediate from the envelope theorem. So remember the envelope theorem. There's another important theorem in every optimization problem. So the envelope theorem tells us the derivative of the value function, the way to find the derivative of the value function with respect to one parameter, say p sub k. So we first take the partial derivative of the objective function. Objective function is p dot y in profit maximization problem. Okay, so if we first take the partial with respect to p sub k, we obtain y sub k. Okay, and then envelope theorem tells us the exact responsiveness of the value function is going to be partial derivative of the objective function evaluated at the optimal solution. So in place of y sub k, we substitute the optimal solution to PMP. That is a supply curve, supply function for good k. Okay? So we obtain the Hotelling's lemma, immediate from the envelope theorem. And just one more thing about the intuition for convexity. That is pretty similar to y expenditure function is concave with respect to price. Okay? So we compare the shape of the expenditure function and the supporting line. Because expenditure function, so along this curve, we adjust our demand schedule. When some price of good changes, say p sub k. Okay? So if p sub k changes, on this curve, we adjust the demand schedules in response to change in P sub k. That should give us the lower value than this line segment, because in this line segment we fix the sum, so we fix the demand schedule. Okay, so here if we compare the profit function and the supporting line, so in this supporting line we pin down the production plan. Okay, so the production plan is fixed by, say, the output schedule and the input schedule fixed by Q star and Z star. Okay, so this line segment tells us the change in profit as the change in the output price, holding the output schedule and input schedules fixed. Okay? Let me call this passive profit function. Okay? But along this curve, we adjust the production plan in response to change in output price. Okay? So by definition of profit function, it gives us the highest profit attainable. Okay? So that should be above the supporting line. So it should be convex like this. Yeah. Alright, so that is a brief discussion about the profit maximization. And in the live lecture next Wednesday, let me show you some more examples. Okay, so hope you enjoyed this video, and then in the next one I will explain the cost minimization.